like palladium, platinum and nickel, the hydrogen can undergo addition to the alkene you get alkane. If you look at the reaction, as I mentioned earlier, the reaction is stereospecific. The both hydrogen atoms come the same side of the alkene. It can be the bottom side or top side. This in addition takes place, and in this reaction, as I mentioned earlier, what happens? You have the metal surface. The metal surface, the hydrogen is adsorbed first. Then your alkene also adsorbed on the metal surface by you have the carbon-carbon double bond. There will be interaction between the bi bond and your metal. Now, once for example, when you pass hydrogen, the hydrogen will be adsorbed to the surface of the metal, and when you add alkene, the alkene now it can also adsorb, it can interact with your metal. You have the alkene here. Now, the hydrogen whatever adsorbed from the metal surface can be transferred to the alkene. You will get the metal alkyl intermediate. You have this kind of intermediate. Now, another hydrogen, when since the reaction is carried out in the presence of hydrogen pressure, another hydrogen can bind here. This hydrogen can transfer again. You will get your alkane. The both hydrogens are added the same side of the alkene. The reaction is syn addition reaction stereospecific. So, when you have different substituents, the reaction of course you will get the selective addition product. So, the next example is addition to halogen. It's a electrophilic addition reactions, and like when you have the alkene, for example ethylene, when you react ethylene with, for example, Br2 or chlorine, under this iodine does not undergo addition with alkene normal conditions. However, bromine readily undergo reactions in the presence of in CCl4. When you carry out the reaction, the bromine undergoes addition to give the vicinal dibromo compound. And similarly, chlorine also can be added. You get 1,2-digaloalkanes. So, in these reactions, if you regarding the mechanism, let us see the bromination reaction. Alkene the double bond attacks the bromine. You get brominium intermediate. So, this brominium ion intermediate undergoes reaction with this Br minus. It acts as a nucleophile. It attacks this. It can attack this carbon or that carbon. Suppose if it reacts here, this anti to this bromine, you will get this 1,2-dialoalkanes. So, if you look at this compound, this also stereospecific reaction, this addition of the bromine takes place anti addition. If you look at it, and this is just opposite to this bromine, you get this anti addition product. Suppose if you react with this alkene trans to butene with the bromine, you will get this dibromo 2,3-dibromobutane. On the other hand, if you have this cis-2-butene, it can lead to mixture of enantiomers. You will study the stereochemistry of these reactions in our in higher class. Depends upon the substrate. When you have this kind of substrate, then you can get stereoisomers. You can get enantiomer in this case. Of course, in this case, you will get a compound which has planar symmetry, and it is a meso compound. We will study in details in the higher class. The next reaction is addition of hydrogen halides to alkenes. This also electrophilic addition reaction. Just we have seen the addition of bromine to alkene is an example for electrophilic addition reaction, and in this case the reactivity of alkyl halides is hydrogen iodide is more reactive comparing to HBr. HBr is more reactive comparing to HCl. This is the reactivity order of hydrogen halides towards alkenes. Now, let us take HBr. If you react with symmetrical alkenes, so you will get 2-bromobutane. Other hand, if you take unsymmetrical alkenes, for example, propene. When you react with propene with HBr, so you will end up with mixture of compounds. There is a possibility of formation of these two compounds, and however, in this case, this will be the major compound. This will be a minor product. So, let us see the mechanism of the reaction we can understand. So, I mentioned this is an example for electrophilic addition reaction. So, the alkene reacts with this HBr to generate the carbocation intermediate. So, this carbocation intermediate reacts with the bromine Br minus the addition product. So, if alternatively it can also form a primary carbocation So, in this case, if the carbocation reacts with the Br minus, you get the primary alkyl halide. So, there is a possibility of formation of both these carbocations. However, the secondary carbocation is more stable comparing to the primary carbocation. So, the formation of this predominant in this case, therefore, and we get this as a major product. This because we will study in the higher class again that when you have the more substituted carbocation, for example, tertiary carbocation or secondary carbocation, they are more stabilized by hyperconjugation as well as inductive effect, and this therefore, this more stable, the concentration of this formation of this carbocation is higher than this. Therefore, we get this as a major compound. So, during 1863, the Russian scientist is called Markovnikov. He studied a reaction of a series of experiments with this substrate. He found that, he observed that, and so the electrophilic addition reactions like addition of hydrogen halide to alkenes, and always the Br minus, the negative ion species undergoes addition to the carbon which has less hydrogen atoms, and in this case if you look at it, this has the one hydrogen atoms. Therefore, the Br minus undergoes addition here and you get this a major compound. This we call it as, it follows the Markovnikov rule product. So, it depends upon the reaction conditions, and alkenes can undergo addition with the hydrogen halides, for example, hydrogen bromide to give the more substituted alkyl bromide. On the other hand, if the reaction is carried out in the presence of like peroxides, you get the opposite addition product, otherwise regioisomer. And let us look at this reaction. When you react with propene, with hydrogen bromide, in the presence of peroxide, you get a mixture of compounds. This is a major product, this minor product. Just we have seen the case of electrophilic addition reaction, always this is the major product. However, when you carry out the reaction in the presence of peroxide, this is going to be the major product, this is going to be minor product. This is called anti-Markovnikov product. And in this reaction, particularly when you carry out the reaction in the presence of peroxide, you get this as a major product. Now, let us look at
Welcome back to this unit on thermodynamics, and we will go through today about the criteria for spontaneous processes, and we will introduce entropy and Gibbs free energy. Just to recap what we have learned in last class, and so basically we have learned that reaction enthalpy of reaction or heat of reaction is total energy of the enthalpy of the product minus total enthalpy of reactants. So, if I just plot in two axes, x axis is your reaction coordinate, if this is your reactants, and say here you have products, corresponding energy level is this. So, if this is H P is the total enthalpy of the product and H R is the total enthalpy of the reactants. This is H in y axis, x axis is reaction coordinator. So, in this case we are writing H R is total enthalpy of reactants and HPR is total enthalpy of products. Then in this case the reaction enthalpy of reaction delta R H is given by this difference, and this is product minus reactants is a negative value. So, this is exothermic reaction. Similarly, if I have the other case where I have again reactants and products, reaction coordinate. In case I have product reactants at lower level, so H R, and products at higher level H P. So, the difference is this. So, this difference is the product total enthalpy. So, this in this case this is the enthalpy of reaction is greater than 0. So, this is a endothermic reaction, endothermic, and this is a exothermic reaction. Now, as we explained that this we cannot always we need to keep the reactants and products in a standard state for comparing the values. So, we defined that standard heat of reaction or enthalpy of reaction, where all the products and reactants are at their standard state, is given by summation of the enthalpies of products minus summation of enthalpies of reactants. So, this is standard molar enthalpy of the products, and this is standard molar enthalpy of the reactant. So, if you multiply it by number of moles, which are the stoichiometric coefficients in the balanced reaction, this gives you the standard heat of reaction, where both the reactants and products in their standard state and a particular temperature T. Now, we also showed later on that you can express this in terms of the heat of formation of products minus standard heat of formation for reactants. And these values, this heat of formation for products and reactants are available in literature, and some are there in your book, as I have taken from NCERT book. You can see this table. In this case, you can see those the heat of formation, standard molar enthalpy of formation of heat of formation is at 298 K or 25 degrees centigrade is given for several substances. Now, sometimes for gaseous reaction, if you do not have the values for this enthalpy of formation, you can get the standard enthalpy of reaction from bond enthalpies of reactants minus total bond enthalpies, this summation bond enthalpies of products. In this case, it is reactants minus products, and how it is arrived we have talked, we have discussed in last class, and this is for applicable for gaseous reactions. So, if you know the bond enthalpies for compounds, we can get delta R H naught, standard enthalpy of reactions, and some of the values are available in literature, and this is some are shown given in your book. So, we later on we continued on discussion, and in this case, as I said that this we are not talking about number of moles in the reaction, it is just balance equation. So, this is the extensive quantity, and the balance equation stoichiometric coefficients are number of moles, and if you reverse the reaction, the value it will be negative of that. Then we continued and discussed other reactions like heat of formation, standard heat of formation at a particular temperature. That we talked about standard heat of transition, and which are many types like fusion, vaporization, sublimation, and we talked about combustion, we talked about atomization, we talked about solution, we talked about reaction enthalpy for ionization. So, ionization enthalpy. We also talked about electron gain, enthalpy for electron gain, and this all these are for 1 mole of substance. Okay. So, these are all intensive quantities, because here we are making sure that we are dealing with 1 mole of compound, either it is formation, combustion, vaporization, all this is related to 1 mole of substance. Then we also talked about thermochemical equation, which is nothing but the actual reaction plus the reaction enthalpy of reaction, standard enthalpy of reaction values. Then we talked about Hess's law, and we talked about Born-Haber cycle. This we based, this the basis of these two was that delta H naught or delta H is an state function. So, it depends or it does not depend on the path. So, these are basically what we discussed in last two classes. Now, we go back and look at the first law again, first law of thermodynamics, which says that when one form of energy is converted to another, the total energy is conserved. That is the first law of thermodynamics. So, we have said that delta U for isolated system is 0 and delta U for closed system Q plus W, and we discussed what are these term means closed system. Now, what it means that if system is losing some energy, say for example, if system is losing some 10 joule of energy. So, Q system if I write as minus 10 joule because it is losing some energy, then surroundings if I write Q surroundings, it will absorb the same amount of it. So, it will be plus 10 joule. So, total Q it will be 0. So, basically no energy is created or destroyed here, only 10 joule of energy got transferred to the surroundings. This is what exactly the first law says. It does not says, first law does not says about the followings. Whether this transfer I just mentioned, whether the energy transfer will happen at all. If happen, then which direction it will happen? If it at all happen, how long it will happen? Again, if it is happen, then how fast or what is the rate at which this energy transfer will happen. So, basically these are 4 questions is not answered by first law. So, what we will do today's discussion will able to answer us the first 3 questions, but this is the rate at which energy transfer or reaction happened is not part of thermodynamics, it is part of kinetics, okay, which is not subject of this topic of this unit.
4,000 bars. Thus, we can see this is a very high pressure that will be created in water. In achieving this pressure, an electric motor of 50 to 100 horsepower rating is used. Now, let us see what is an intensifier. It accepts the water at low pressure, typically at 4 bar, and expels it through an accumulator at high pressure, that is approximately 4,000 bar. It works through a hydraulic reciprocating mechanism which is responsible for intensifying or enhancing the spread of the fluid. Then what?
Gas expand into vacuum. If I release a gas into vacuum, gas will immediately expand and occupy the total volume. Hot object, if I keep a hot object
high
in a surrounding
pressure to the head. They are of 6 to 14 millimeter in diameter depending on the application in which we are using it, and it allows for flexible movement of the cutting head. Jet cutting nozzle. These nozzles are used to convert the high pressure liquid into high velocity.
Is a hot pen, like the temperature is high, if we
Indicated. This is the unit where this pressure, high pressure will be converted into high velocity. It provides a coherent water jet stream for optimum of low density soft materials, which is considered unmachinable by conventional means. As such, there is a strong possibility of erosion in the orifice of the nozzle due to high pressure of liquid in water jet machining and that of abrasives in abrasive water jet machining. As I told earlier, this
fuel burns spontaneously. So, these are the some
very high pressure. At this stage it will be of high pressure, and at this stage while discharging it will be of very high velocity. Therefore, there is every possibility that this jet wall may get eroded or some deteriorations on this jet wall will take place because of this high velocity fluid passing through this. Also, if this is AWJM, abrasive water jet machining, then in addition to this water there will be abrasive particles mixed in this, and this jet walls, these jet walls are the materials which will have to withstand this pressure of this fluid as well as the impact of these abrasive particles. So, these are abrasive particles, abrasives. Now, because of this continuous impact of these abrasives and this flowing fluid, these jet walls may get eroded very frequently, and this is one of the major problems being encountered in this system. Therefore, the choosing the material, right material for this jet or this nozzle is a very big question. Generally sapphires are used, which are considered to be a very good material as far as this nozzles are concerned. Therefore, a high wear resistant material such as synthetic sapphire is used as nozzles, as I have already told, and a picture is there in the screen also. This is how it works. This is the abrasive powder or abrasives, and this is the high power high velocity water coming out, and this is where it gets mixed, and this jet or this nozzle walls will have to bear this pressure as well as the abrasive action of these abrasive materials while enabling this jet or this mixture of high pressure water as well as the abrasives through this. Let us see the functions of the drain or the catcher. It acts as a reservoir for collecting the machining debris and trained in the water. It also helps to reduce the noise level associated with the reduction in velocity of water jet. Now, let us look into the factors that affects water jet machining performance. These factors are generally grouped into three major categories. These are Z or nozzle based parameters or factors. Here the Z diameter or the nozzle diameter is one of the major factors. So, higher the diameter of this nozzle, so there will be possibility that the nozzle, the water stream coming out through this nozzle will get diversified more, or there will be more diversion in this case. And then the standoff distance, as we have seen in case of abrasive Z machining, the standoff distance, which is the distance between the Z opening and the target material. So, this is a very critical parameter. So, depending on this, the energy with which the particles, the energized water particle and the abrasive particles will hit the target will depend upon, and therefore, accordingly the performance of the process will also vary, and there has to be an optimized distance for this standoff between this nozzle and the target. Then the next category is the Z fluid. Here the type of the fluid, which fluid we are using, it may be water or it may be other liquid also. However, water is always preferred, low cost, and it is operator and environment friendly, and of course available also. Then the velocity of the fluid, which is very critical. This velocity will give the energy to the particle or the working energy, then the flow rate at which it is flowing, then the pressure of this fluid, then the viscosity of the fluid. If the fluid type changes, then the viscosity will also change, but if it changes appreciably, then one has to have some mechanism to maintain the viscosity, so that with temperature or other factors it does not get changed during the working hours. Then the third category is the workpiece related parameters. So, here what is the type of the workpiece, then the thickness of the workpiece, and then the feed rate of the workpiece. So, it is to be mentioned here that the thickness, if it is a very high thickness this workpiece, then the process may not be very efficient in this case. So, all these three categories of parameters will affect the final outcome of this process, which is either cutting or the finishing or the cleaning of the target surface. Let us see a few parameters, like what are the cutting rates for various materials, like leather. For leather of thickness say 2.2 millimeter, feed rate used is 20 meter per minute. Similarly, if the material is vinyl chloride and a thickness of 3 millimeter, the feed rate suggested is only 0.5 meter per minute. Similarly, for polyester of 2 millimeter thickness, the feed rate is 150 meter per minute. For Kevlar of 3 millimeter thickness, only 3 meter per minute. Then for graphite of 2.3 millimeter thickness, 5 meter per minute is recommended. For gypsum board of 10 millimeter thickness, feed rate is 6 meter per minute. Corrugated board of 7 millimeter, feed rate is as high as 200 meter per minute. Pulp sheet for 2 millimeter thickness, feed rate suggested is 120 meter per minute. Then for plywood of 6 millimeter thickness, 1 meter per minute feed rate is suggested. Abrasive water jet machining is a subcategory of water jet machining. in which an abrasive is introduced in the water to accelerate the process, as I have already discussed with the help of diagrams. Hence, this abrasive water jet machining process is duly considered